Okay, chapter 19, stoichiometry. I'm just going to focus on one concept and I'm going to show you just a couple of example problems. I think this will be the last video for this chapter. Yeah, this chapter is really the sort of thing that you have to practice it. If you wait until the day of the test to be the first time you've looked at these problems, you're probably not going to get them because they not only involve the gas laws, but they also involve a review of stuff that we learned way back in the fall. So, first thing about stoichiometry, if you have a reaction, let's say we have 2 moles of gas A, and we're reacting it with 3 moles of gas B, and then that's going to produce diammonium tribiide gas, 1 mole of it. If you hold the pressure and the temperature constant, so we'll write pressure constant, temperature constant, then your mole ratios and your volume ratios are equivalent to each other. Now, when I say that, that doesn't mean that they are the same numerical value. In other words, what I'm about to tell you, if we have 3 moles of gas B, that doesn't mean we have 3 liters of gas B. That just means that the ratio of volume for gas B, it's going to require 3 times as much volume as A2B3, which is only 1 mole, which requires 1 unit of volume. So when we look at this problem and we say, all right, let's say we're running this reaction at STP conditions. Okay, so we do our little PV equals nRT. Well, R is a constant. We're holding the temperature constant. We're holding the pressure constant. So although the volume is not the same number as the number of moles, they are in ratio to each other. So if I was to say, hey, we're going to run 2 moles of A with 3 moles of B, and that's going to give us 1 mole of product, I could just as well say, all right, let's say we run a calculation and it requires 100 liters of chemical A. And that means that we would produce 2 moles to 1, half as much. So we would only produce 50 liters of product. It's still a 2 to 1 ratio. Even though the exact number for the volume isn't 2 liters to 1 liter, it's 100 liters to 50 in this case, but it's still in the same ratio. So for B, we would have 150 liters. So we could say in this reaction, we could take 100 liters of chemical A and react it with 150 liters of chemical B. And as long as the pressure and temperature remain constant, then we're going to get 50 liters of our product. Now, do understand, in reality, you're taking 5 moles of particles and you're producing only 1 mole of particles, so you're not getting as many particles hitting the container. So the pressure would change and the volume wouldn't. We'd run it in a container of constant volume. But if we're dealing with an apparatus, like for instance, my goodness, why does the word escape me? Where we have a piston chamber, let's say, where the piston can slide up and down in the chamber, then that piston would move based upon this chemical reaction, and it would move in the volume ratio that would be equivalent to the mole ratio in the reaction. So one of the shortcuts that you can make in these stoichiometry problems is if they run it at STP, for instance, and you have 1 liter or 2 liters of chemical A, you can very quickly surmise that you need 3 liters of chemical B and that you're producing 1 liter of product. The mole ratios and the volume ratios are equivalent to each other. All right. Stoichiometry problems. Let's start with one. We said that back in the day with stoichiometry, one of the things, first of all, we need a balanced equation. And the problems here, they don't give you a balanced equation. In the book, they don't give you a balanced equation. I would never do that on a chemical test for Chem 1 honors. I wouldn't combine both equation writing skills and stoichiometry skills and gas law skills in the same problem. That's more of an AP level type of problem. So we would go ahead and give you the reaction. Here, propane is combusted, so prop means 3 carbons. And we double the carbons and add 2 to get the hydrogen, so it's C3H8, and that's a gas. And we're going to react it with oxygen. Now this is molecular oxygen, so it's O2. And all combustion reactions produce carbon dioxide and water. Again, a good review for the final exam if we were to have one. We're not. In a normal year, we would. So I kind of construct it this way for that purpose. We go and we balance this equation. We get 3 moles of carbon and we get 8 moles of hydrogen. So that gives us a total of 10 moles of oxygen. So there's our balanced equation. And let's see what we got here. We are reacting 22.6 liters of propane. Now you got to get used to describing gases not just in terms of mass or moles, but in terms of volume or pressure. So this particular container would be 22.6 liters of propane at a certain temperature and pressure. Now, to do a stoichiometry problem, we need to know the moles of propane, but we certainly can get it from this. We just do a little PV equals nRT. Now, in a stoichiometry problem, first thing we have to do is determine whether or not we are dealing with a limiting reagent or an excess reagent. And we said that if they only mention one reactant, then by definition, that's going to be my limiting reagent. And then we would say that the propane is limiting, LR, limiting reagent. And since they don't mention how much oxygen, we're going to assume that is the excess reagent. So we just have to deal with the propane. So I'm going to solve for moles of propane, and that'll be PV over RT. And the pressure is given. The volume is given. We had started with 22.6 liters of propane. And the gas law constant is 0.0821 liter atmospheres over moles Kelvin. And the temperature is given at 285 K. All right, so when I do that calculation, I get 1.073 times 22.6 divided by 0.0821 divided by 285. I get 1.04 moles of propane. Okay, so I'm off to a good start. Now I have to use the balanced equation in order to calculate how many moles of water vapor I need, because that's what they're asking me, mass of water vapor. If I know the moles, then I can convert that to grams. So start with what they give you, 1.04 grams of propane, multiply by a fraction. We're going to convert grams of propane into moles of propane. Now I put 1 mole of propane because that's how many moles are in the balanced equation. So let me rephrase. I converted 1 mole of propane because that's how many moles are on the periodic table, right? It's 1 mole. So we can look up propane on the periodic table. It's 3 times the mass of carbon plus 8 times the mass of hydrogen. And that gives me 44.097 grams. Now, once I do that, then I can use the balanced equation. According to the balanced equation, 1 mole of propane is going to yield 4 moles of water vapor. And then once I know the moles of water vapor, I can use periodic table again to convert that to grams. So 1 mole of water, I look up hydrogen and oxygen, add them together, and now I can get my mass of water. 1.04 times 4 times 18.015 divided by 44.097. And I get 1.69948. Okay, so that's going to be 1.70 grams. Okay, so a review of stoichiometry again. In order to use the balanced equation, we need to know the moles of the limiting reagent. In this case, propane was the only chemical mentioned, so it had to be the only reactant, so it had to be the limiting reactant. So we're going to start with that. We didn't know the moles of propane, but we did know everything else we needed to use PV equals nRT to get moles of propane. Once we had mole propane, we converted to grams. Wow! I just did this whole problem entirely wrong. Shame on me. No, I said because look, this is wrong. Son of a gun. 1.04 moles. I didn't have to do that conversion. Shame on Burnett. Look at this. That's terrible. That's terrible. All right, they gave me moles. Start with what they give you. Don't even need a fraction. See, now I'm all upset. Start with what they give you. 1.04 moles of propane. Now we can convert that using the balanced equation. Moles of propane to moles of water. And then for every 1 mole of water, 18.015 grams. So that changes that calculation. So sorry. I would edit if I had any sort of editing skills. And you know, sometimes we can learn from mistakes though. Easy to make that sort of mistake. I got in the habit of doing stoichiometry problems the way we did back in the fall. And back in the fall, remember I told you not to memorize the pattern. Now she wound up doing what I just did. The pattern back in the fall was start with grams, convert it to moles, use the balanced equation, then convert back to grams. And I fell for it, my own trick. So no, we got to focus in on what we got. PV equals nRT gives me moles of propane. From there, I can use the balanced equation to convert it to moles of water. And once I have moles of water, I get grams of water. How embarrassing. All right, anyway, limiting reagent problems. Now, in a limiting reagent problem, the way you know that it's limiting reagent is not because they put the words limiting reagent in front of it, but because they mention values for both reactants. And they're saying, all right, we're going to use 20 grams of hydrogen. We're going to use 78 grams of nitrogen. Now, it's very unlikely that those masses are going to be in the perfect mole ratios. One of them is going to get used up, and then the other one is going to be in excess. It's a matter of, well, which one is the limiting reagent? And the limiting reagent is the one that produces the least amount of product. So I'm going to write that. Limiting reagent yields minimal product. So we got to see how much product we get here. So we're going to actually stoich this thing twice. Let's start with the hydrogen. If the hydrogen was the limiting reagent, we'd start with 20 grams of the hydrogen. And we would convert that to moles. And then according to the balanced equation, for every 3 moles of hydrogen, I produce 2 moles of ammonia. Now you can convert this to grams if you want. I think it's an extra step. Until you figure out which is the limiting reagent, I would hold off on converting to grams. So we do 20 divided by 2.016 times 2 divided by 3, and I get a total of 6.61 moles of product. So now I'm going to go back and I'm going to do the same thing. Except for now I'm going to see what happens if nitrogen was a limiting reagent. So we have 78 grams of nitrogen. We're going to convert that to moles. So I look up nitrogen on the periodic table, multiply by 2 because there's 2 nitrogens in a molecule. And then I use the balanced equation. 1 mole of nitrogen gives me 2 moles of ammonia. So we do 78 divided by 28.014 times 2. And I get 5.57 moles of ammonia. So what happens in this reaction is that the 5.57 moles is my yield because 78 grams of nitrogen are going to be consumed at that point. Not all 20 grams of the hydrogen will. We'll have some hydrogen left over as the limiting reagent. But the one that produces the least amount of yield is my limiting reagent, and that's the one I use to calculate my final yield. So I'm going to take the 5.57 moles of ammonia, and now I'm going to convert that to grams for my answer. All right, so 1 mole of ammonia is 14.007 plus 3 times hydrogen. And I get 17.031. Okay. And then multiply that by my yield, which was 5.57 moles. And that gives me 94.9 grams. So my actual yield is 94.9 grams. Now, Why did I want to show you this problem? All right. At the type of problems that you're going to get on this test, however, they're probably not going to give you the grams. What they would do is they'll give you something like this. Let's say we're running the same reaction. All right, 3 moles of hydrogen plus a mole of nitrogen, and that's going to produce 2 moles of ammonia. Okay, so at STP, we're going to react 4.47 liters of nitrogen with 12.17 liters of hydrogen. They want to know what is the volume of ammonia produced. Okay, so let's do that then. So I said that at STP, you're holding the temperature and the pressure constant. So under these conditions, volume ratios are approximately the same as the mole ratios. So this is pretty easy to find out the limiting reagent. We take the hydrogen, we do 12.17 liters of hydrogen, and now we could just use the volumes in our equation. Now we could also use this factor, that 1 mole of any gas is 22.4 liters, but you're going to see that you're going to get the same answer either way. So if you recognize constant temperature and pressure, mole ratio and volume ratios are constant. So we could say that this is 3 liters of hydrogen will produce 2 liters of ammonia. So we'll get 12.17 times 2 divided by 3, and I get 8.113 liters of ammonia. Now let's do the same thing for the nitrogen. 4.47 liters of nitrogen. And we use the volume ratios, mole ratios to be the same. So 1 liter of nitrogen would produce 2 liters of ammonia. And we get a yield of 8.94 liters of ammonia. So in this case, even though we had a large number, 12.17 liters, this is actually my limiting reagent, and this is my yield. That would answer the question. Now, they're most likely to ask you, instead of volume of ammonia, what if they asked you mass of ammonia? Well, from there, we have STP conditions. So under STP conditions, we could say 1 mole of any gas is 22.4 liters. So if I have 8.113 liters of ammonia, I can convert that to moles. 22.4 liters gives me 1 mole of ammonia. And from there, I can convert that to grams. So 1 mole, 17.031 grams. So 8.113 divided by 22.4 times 17.031, and we get a mass of 6.17 grams. So the two things I wanted to illustrate by showing you this version of the problem. First problem was to just review what limiting reagent is and the procedure. You have to stoich it for both reactants and figure out which one is limiting. That's the one that gives you your yield. Second, mole ratio, volume ratios a lot of times are equivalent when you're holding it at constant temperature and pressure according to the Avogadro principle. So again, I can make the shortcut here of starting out with 12.17 liters of hydrogen and then using the volume ratio instead of mole ratio. And then a shortcut to get from liters to grams at STP is to use that conversion. 1 mole of any gas is 22.4 liters. Okay. All right, so we got 2 more problems I want to do. And let's see if I can do these really quickly. You should try this on your own. Carbonic acid decomposes to create water vapor and carbon dioxide gas. If 14 grams of water vapor is produced, at STP. What's the volume of carbon dioxide produced? Again, this is at STP, so give it a shot, and I'll pause and wait for you to come back. Hey, welcome back. Okay, so I'm going to start with what they give me. We have 14.0 grams of water. And to use the balanced equation, I'm going to have to convert that to moles. So I look up the mass of water, which is 18.015 grams. That gives me 1 mole of water. And then according to the balanced equation, 1 mole of water gives me 1 mole of carbon dioxide. And they want to know what volume of carbon dioxide. Well, a couple of things here. PV equals nRT I could use to get volume. If I know the moles of carbon dioxide, I know at STP what the temperature is, what the pressure is. Another thing I can use at STP, 1 mole of carbon dioxide would occupy 22.4 liters. So I'm going to do this calculation, and I'm going to use the shortcut. 1 mole is 22.4 liters. Again, remember though, with that shortcut, that's only under STP conditions. So this comes out to be 0.777 moles carbon dioxide, and now I'm going to convert that. And we know that 1 mole of any gas at STP is 22.4 liters. So it's going to be 0.777 times 22.4, and we get 17.4 liters of carbon dioxide. Okay. All right, now the last problem. A little bit of lab, since we didn't get to do this lab, which is a shame because it's a very cool lab. Let's say we're going to take a piece of magnesium metal and we drop it into a strong acid like hydrochloric acid. Now the hydrochloric acid is in excess, and we're going to use 21.2 grams of magnesium. So this I'm going to label this my lab data. All right, 21.2 grams of magnesium. When I'm done, and when I dry it through a desiccator to get out the water vapor that evaporates, I get a yield of 23.52 liters of hydrogen. The pressure gauge for the room is 764.6 millimeters mercury. The temperature of the room, 21.8 degrees C. What is the percent yield? Okay. Start with what it is that we're actually trying to find. Percent yield is equal to actual yield divided by theoretical yield. And then we have to multiply that by 100%. Okay, so do they give us any of this? Yes, we know the actual yield. It's 23.52 liters. That's what we got in the lab. All right, so we're getting there. Now the theoretical yield is going to be based on the stoichiometry. All right, so I'm going to have to make a couple conversions here first. I know the volume of the hydrogen. I know the pressure. I know the temperature, but let's convert this temperature to Kelvin. So if we're going to get Kelvin temperature, we're going to have to do Kelvin equals degrees C plus 273. And that's going to give me 295 Kelvin. All right, so if I want to get the theoretical yield, I have to figure out the volume that would have been produced. So PV equals nRT. The volume that should have been produced under perfect conditions would have been nRT over P. So how many moles of the hydrogen are we dealing with? Okay, well, we don't know that. But what we do know is that we started with 21.2 grams of magnesium, and that for every, according to the balanced equation, for every 1 mole of magnesium, we produce 1 mole of hydrogen. So I'm going to make that conversion. 21.2 grams magnesium. And then I look up the mass of magnesium, which is 24.305 grams for every 1 mole. And according to the balanced equation, for 1 mole of magnesium, we produce, wow, I wrote mercury. For 1 mole of magnesium, we produce 1 mole of hydrogen. So how much hydrogen should have been produced? 21.2 grams divided by 24.305, and we should have gotten 0.872 moles of hydrogen. Okay, so we take the 0.872 moles of hydrogen, and that becomes our theoretical yield. Multiply it for the gas law constant for millimeters of mercury, so that would be millimeters of mercury liters over mole Kelvin. The temperature, 295 K, and the pressure was 764.6 millimeters of mercury. All right, so what volume should we have produced? 0.872 times 62.4 times 295 divided by 764.6. And I get 21.0 liters. But we collected 23.52. Okay, let's change that because I designed the question wrong. Let's say that what we collected was actually less than 21 liters. Let's say poorly designed question. I went in the wrong direction with my value when I designed the question. 19.52 liters. Let's say that's what we produced. Now we can do actual yield, 19.52 liters, divided by a theoretical yield, 21.0 liters, times 100%. So 19.52 divided by 21 times 100%, we get 93.0% yield. Right. And those are the basic types of problems we have. Let's go back real quick through them. First type of problem we said was, remember, mole ratio and volume ratios held at constant temperature and pressure are approximate to each other. We need a balanced equation. A lot of times they'll give you a problem where they give you an amount, and we have to remember that volumes and pressures of a certain chemical are amounts. In this case, they gave us the volume of propane. We knew that was the limiting reagent, so we converted that to moles, although I did it wrong. And then we took the moles of propane, used the balanced equation to get mass of water vapor. Second type of problem, limiting reagent. If they don't tell us what the limiting reagent is and they give us multiple reactant values, then we have to stoich them to figure out which one produces the least amount of yield. And then we can use that to get our final answer. I now realize, wow, what a bad day for me. Look at the question. It says what volume of ammonia is produced at STP. I did mass of ammonia. So did that problem wrong. And then we said that if they give you a balanced equation and you're doing limiting reagent, remember, if it's at STP, we can use a couple shortcuts here. One, volume ratios, mole ratios. And second shortcut was that 1 mole of any gas is 22.4 liters. And then we did this, hey, here's a easy stoichiometry problem, but we're going to use the shortcut for 1 mole, 22.4 liters. And then the last problem was, if we have a yield and we have some lab data, can we do a percent yield? And the answer is yes. We use PV equals nRT to figure out the volume that should have been collected, and we compare it to the volume that was collected, and that gives us our percent yield. And that's it for chapter 19. Again, it requires practice. Make sure you look at the practice problems. I'll probably do a short review video. And thanks for bearing with me on this one. This was not my best work.